let's go ahead and figure out how to do this problem. So like last time, when we're thinking, or I should say, when you see an integral and you think you might want to use U-substitution, your job is to look for something that's probably stuck inside some other function, and more importantly, whose derivative is also there. So the seemingly obvious candidate here would be letting u equal x to the 6 plus 2, because it's stuck inside the square root, and because its derivative, du dx, is equal to 6 times x to the 5th. And we essentially have that, right? Again, we don't really care about constant multiples. You can always adjust for a constant multiple. So that's 6, I'm going to kind of ignore, like, oh yeah, I definitely have a derivative that's x to the 5th in it. There's my x to the 5th right there. So the next part is where people do this in a myriad of ways. My preferred way of doing this is to make the thing I have here look like what I have in my integral. So I would really like to do it this way. I'm going to say that du equals 6x to the 5th times dx, and then 1/6 du equals x to the 5th dx. That's my preferred way of doing it. But for this problem, I'll show you all 2 other ways you can also approach this, which are both perfectly fine. So I'm going to rewrite this as the integral of, let's see, the x to the 5th dx, whoops, back pen. The x to the 5th times dx, that's going to be my 1/6 du. And I would always recommend dealing with changing dx into du whenever you're doing a U-substitution first. That's the first most important part. I like to put the 1/6 on the outside, and of course the du on the inside. And then the rest of it's just going to be the square root of u. That's the way I would do this. Before we finish though, let me point out 2 equally valid ways of doing it. So another way people like to do this is they say, I have this integral of x to the 5th square root of x to the 6 plus 2 dx, and I'm going to use this instead and say, I really wish I had a 6x to the 5th. Well, we can make that happen. Multiply by 6. Can't just multiply by 6. What else do I have to multiply by? To balance it out. But this is exactly the same thing, right? If we do this, now my 6x to the 5th times dx is my du, and I'm going to have this equal to 1/6 the integral of the square root of u times du. Same thing. Alternatively, some people like to do this thing where they actually isolate dx completely. They say, I'm really going to just divide everything by 6x to the 5th. And so I'm going to say du divided by 6x to the 5th is equal to dx. This pen is not great. So in that case, they would take the integral x to the 5th times the square root of x to the 6 plus 2 times dx, and replace the dx with du over 6x to the 5th. And this certainly looks kind of wrong in that your integral has x's and u's, and then we have to keep going. We need all u's or all x's. But what we see here is the x to the 5th here can cancel with the x to the 5th down there. And then the remaining integral is, well, I've got the square root of, that's going to be a u times a du over 6. It's very, very common practice to always bring constant multiples out to the front of the integral. But I want to point out that no matter which way you do this process, whether you do it like I like to do it and you try and make the inside of the integral look like what you have, or you solve for dx, or you wish you had the right constant, it still turns out the same. In each instance, we are always going to get 1/6 times the integral of the square root of u. So what I'm really trying to point out is it doesn't matter which way you do it. We're all going to get to the same place. I'm going to continue to probably do it in this first way that I like, but if you want to see something else, you can let me know. So this is going to be, I would probably encourage you to rewrite this as u to the 1/2. And then that's going to be 1/6 times, let's see, add 1 to the 1/2, you get u to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. And then 1/6 times 2/3 is 2/18, which is 1/9. Plug back in x, or sorry, what u is equal to, which is x to the 6th plus 2 to the 3/2 plus c. That is the antiderivative of x to the fifth times the square root of x to the sixth plus 2. Questions? Yeah, I should point out, right? No matter which way we do it, and the reason I mentioned these kind of 3 different ways of doing it is because people just see it differently. Some people really like doing this thing where you multiply by 6 and then by 1/6. Some people really like doing this thing where you solve for dx. I will say solving for dx doesn't always work out so great. A lot of the times it will, but sometimes it doesn't. So yeah, most of the time you can make it work. If it, I should say, if the problem is a U-substitution, yeah.
Why don't you multiply the 6 out to
That's a fair point. So the reason we don't do that is because 1/6 times a constant is still going to be a constant. So 1/6 times c, I would just call it a new c. So we just kind of don't bother. But you're not wrong to say that we could do that. And it's actually something, so that specific thought there, where you multiply the coefficient times the constant, that's going to come up in 16C when we start solving differential equations, and you're actually going to have a function that gets multiplied by that constant. And to really make sure to, it's really important to make sure that that function that's out in front of your integral does get multiplied by that constant. So when we see where we're in 16C, if you have to take 16C, that's definitely something that will come back where you actually do have to be really careful. So to keep that in mind, it's going to come up in the next math class. But for this one, a constant times a constant is still just a constant, so we don't worry about it. All right. So let's look at some more examples. Let's look at the integral of e to the square root of x over the square root of x. And here I'm thinking I probably need to, well, I know the integral of e to the x is e to the x. I wish I had just something like e to the u. So it would probably make sense to let u equal the square root of x. For the same reasons as before, in that it's stuck, right? That square root of x is stuck in the exponent. So I'm always looking for the things that you could also argue the square root of x is stuck in the denominator. So it's in two places, it's probably a good choice for you. Here is where, well, in fact, let's talk about it. So my du is going to be 1/2 x to the negative 1/2. So most of the time it's pretty standard to just start off by writing du equals your derivative times dx. I've been writing du dx equals the derivative, but we kind of usually just jump to this spot here. And if you wanted, you could write this as 1/2 root x dx. And what I want to point out is here's a problem where it's really, really important to make sure you deal with transforming the dx into du before you do other stuff. Because if you were looking at this, you might think, oh, I'm going to do the integral of, well, let's say I've got e to the u over u, right? Because u is the square root of x. And then the dx part is problematic, right? I can't just change dx into du times 2 root x. I mean, you could actually make it work. It would work out just fine, but it's more trouble than it's worth. So what I really want to say is we need to make this show up. Well, I pretty much have that. Right? I have a dx over the square root of x. I just don't want that 2 there. So I'm going to multiply both sides of this by 2. It's a 2 du equals 1/√x times dx. And then recognize that, oh yeah, that right there, that is equal to 2 times du. So then we can rewrite the integral as the integral of e to the u times 2 times du. And yeah, I should have just brought the 2 out in front. And then e to the u is the best. Its antiderivative is just itself. So I'm going to get 2 times e to the u plus c. And you're right, you could put parentheses around that and say it's 2 times all of it, but then you're going to get 2 times e to the u plus 2c. And we're just going to call that a new constant. So this is, except we're not going to call it something different. We're just going to call it c again because we're super lazy and we want to use all the same letters as much as we can. And then we should plug back in square root of x. So there's our antiderivative of e to the square root of x over the square root of x. We're always using this idea of looking for a thing that's stuck somewhere, and also its derivative should show up. Those are the two things that, and I should really say they don't both have to be true. In fact, neither of them actually have to be true to do a U-substitution, but those are the things we look for. There are guides when we're doing a U-substitution. Let's look at, why don't you all try this one? Oh, that's interesting. That's not be there. Okay. So let's try. I want you all to give this one a shot. I've got the integral of x plus 3 divided by x squared plus 6x plus 1 cubed. Give that one a try. Also, for those of you who have joined, here's the attendance form. And if you need the attendance form in a class, it's right up here. Or you can find it later on campus. You know, you should know at this point where everything is. If you don't, go to that. People at home, you should be working on it too. I hope. I can't make you, but you should. It's good practice. I mean, I can't make any of you do anything, right? You can sit and wait, you can do the problem. Either way, it's fine. So what's the thing that's stuck somewhere? I would say it's x squared plus 6x plus 1. It's definitely stuck in the denominator being raised to the third power. And more importantly, its derivative is 2x plus 6, which is something else we haven't. So you might be like, 2x plus 6, and you're like, yeah, we have 2x plus 6. It's just x plus 3 times 2. So I see an x plus 3 times dx. Sorry, I mean to capture that 3 in there. I'm going to try and make this right-hand side look like an x plus 3 times dx. So I'm going to multiply both sides of this by 1/2. So that if du equals 2x plus 6, 1/2 du equals x plus 3. So this top part here is going to get replaced with a 1/2 du over u cubed. This integral probably bears rewriting. I would much rather rewrite this as 1/2 times the integral of u to the -3rd du. It's going to make it easier to deal with. Yeah. So what I really did was I divided both sides of this by 2. So I could say, like, I'm really doing du divided by 2 equals 2x plus 6 times dx divided by 2. And then really I'm doing this part divided by 2. So 2x divided by 2 is 2, 6 divided by 2 is 3. So this becomes 1/2 du, or du over 2, whichever way you want to write it, equal to 2x divided by 2 plus 6 divided by 2. Yes. That's what I'm doing there. And again, right, I'm trying to make it so that what I have over here looks like what I have in the integral, but some people like to do the opposite thing and say, I want to make the integral look like what I have over here. So an equally valid way of getting there would have been to say, I'm going to take my integral x plus 3 dx over x squared plus 6x plus 1 cubed. And I'm going to both multiply by 2 and by 1/2. So that now this top part here is 2x plus 6 times dx, which is exactly equal to du. And then I would have had 1/2 integral du over u cubed, which is exactly the same as that, just written a little differently. Either way is fine. Do what works best for you. I'm showing you what works best for me because that's what has always worked best for me. So then we're going to get 1/2. If I anti-differentiate this, I'm going to get u to the -2 divided by -2 plus c. And then we're going to rewrite this as -1/4 times u, which is x squared plus 6x plus 1 to the -2 plus c. Or you could write it as -1/4 times x squared plus 6x plus 1 squared if you want to bring it down to the denominator, but it doesn't seem necessary. Yeah. Let's look. Sure. Yeah. No, don't be sorry. Correct. Yes. So far we haven't talked about definite integrals at all. We've only talked about indefinite integrals, where you're being asked of this notation, this indefinite integral is just another way of saying find the antiderivative. And so when you're finding the antiderivative, aka the indefinite integral, your answer is always going to be a function. Specifically, a function using the same variable you start with. So if we start with a function, an integral of a variable with x's in it, we have to end with a function with x's in it, right? We can't stop at what u is equal to. That's not going to be the case necessarily when we talk about definite integrals, where you're finding the area under the curve. But we're not quite there yet. So yeah. And yeah, it's kind of weird. I feel like definitely this material talks about U-substitution before they really talk about definite integrals, which seems a little out of order to me, but it's fine. I mean, it's really fine either way. So let's continue on. If I can, let's look at the integral of e to the 5x over the square root of e to the 5x plus 6. So I'm going to pick u equal to, I could pick u equal to e to the 5x, but typically if you can bring along a constant, it's a good idea too. So I really should pick e to the 5x plus 6. 1, because it's stuck somewhere. And 2, because throwing on the plus 6 isn't going to change the derivative at all. My du dx is still going to be the same whether there's a plus 6 there or not. So my du dx is going to be the derivative of e to the 5x, which is e to the 5x times 5. And then I really want, my pen's to stop disappearing. I really want an e to the 5x times dx to show up. So I'm going to multiply by dx, divide by 5. So the du divided by 5 equals e to the 5x times dx. I'm looking at my integral. I'm trying to make this thing over here look like that. Usually by multiplying or dividing by a constant. So let's see. This is going to equal the integral of du over 5 divided by the square root of u. And typically, this is worth rewriting. I'm going to bring the 1/5 out. Instead of writing 1 over the square root of u or 1 over u to the 1/2, I'm going to write it as u to the -1/2. Because it's always going to be easiest to integrate or anti-differentiate something where it's just your variable raised to a power. So let's see, I get 1/5 u to the +1/2 divided by 1/2 is like multiplying by 2 over 1. And then we get 2/5 times e to the 5x to the, e to the 5x plus 6 to the 1/2 power. Or if you prefer, 2/5 times the square root of e to the 5x plus 6 plus c. Either way is fine to write it. Yeah, okay. We're almost there. Cool. Let's look at a couple more examples. Yeah, we'll do one of those too. So let's look at this one. The integral of sine of x times cosine cubed x dx. Here is an interesting situation. Either choice, when I say either choice, meaning you could pick u equal to sine. What's the derivative of sine? Cosine, which we definitely have a cosine there, right? You'd have to like break one off, but that would be fine. You could write that as cosine squared times cosine. So u equal to sine is definitely a plausible choice. U equal to cosine, what's the derivative of cosine? That's also a plausible choice, right? We definitely have this, we don't care about, right, the negative we can adjust for. And so we could certainly make that work as well. So what's the better choice? U equal to cosine or u equal to sine? Well, sometimes people think sine is the better choice because the derivative is nice, right? We wouldn't have to adjust. But in this case, cosine is the better choice in that you have cosine stuck inside another function, right? You have cosine of x being cubed. So if I rewrite this to make it a little more obvious that you have cosine x quantity cubed, we want to make the choice where u is equal to cosine of x. It's going to require less algebra and less use of trigonometric identities here. You could also let u equal to sine and it would work, but then you're going to have to use the identity where cosine squared equals 1 minus sine squared, which isn't impossible, but it's just more work that way. So if you have the choice, you want to let u be the thing that kind of is more complicated or in something more complicated. So u is cosine and my du is negative sine of x dx. And then I want a positive sine of x dx, so I'm going to say negative du equals positive sine of x dx. All right, so I'm going to rewrite my integral as, so my sine of x times dx is going to become a negative du. And I really, so if you write it in your integral, that's fine, but I'm going to, well, it's kind of fine. I have a negative du and then I have a u cubed. Now, if I write it that way, it looks like I'm writing u cubed minus du, which is not good. It should be u cubed times negative du, which is why I should really just write it as negative integral of u cubed du. Just pull that constant multiple, even if it's a -1 or a negative, out to the front. Negative u to the 4th over 4 plus c. And then we get negative, our u was cosine, so cosine to the 4th x over 4. All right. Let's look at another one. The integral of x to the 4th times x to the 6th plus 1 squared. What seems like probably the only possible choice for you? Yeah, definitely, right? X to the 6th plus 1. That seems like that's the only thing I would think about choosing for you. So let u equal x to the 6th plus 1. Well, I'm not thrilled because our du is going to be 6x to the 5th dx. And although I could certainly divide by 6, I can't really just divide by x to give myself an x to the 4th dx, right? It's not going to work out so well if I do du over 6x equals x to the 4th dx. Because then when I start replacing things, my x to the 4th dx will become the du over 6x. This will become u squared, but I'll still have an x in there. And I don't really want to do, there's something you can do for that, but it's not going to work out. We're going to have problems if we try to replace that x with something that we solve for. Here, the idea is that sometimes you don't have to use the tools, right? We don't have to do a U-sub here. This one we could totally and should just totally multiply it out. So we're going to rewrite this as the integral of x to the 4th times x to the 6th squared is x to the 12th plus 2x to the 6th plus 1. And then if we distribute the x to the 4th, we're going to get the integral of x to the 16th plus 2x to the 10th plus x to the 4th. And then if we anti-differentiate, we're going to get x to the 17th over 17 plus 2x to the 11th over 11 plus x to the 5th over 5 plus c. So sometimes something might kind of look like it could be a u sub, but it's not. And let me actually look at something really quick here. Did you go papers? I just want to look. Let's see one thing. Too crazy here. I'm just looking at your assignment to see if there's any integral of the type that I'm thinking about exposing you to, but I don't think you're quite there yet. So I think we'll hold off on that. Okay. Let's look at one more question and then we will shift a little bit. There's papers everywhere all the time. Yeah, here we go. Oh yeah, this is a great question. So, true or false? The integral of natural log of x dx is equal to x natural log of x minus x plus c. So we don't know how to integrate the natural log of x yet. We definitely will learn how to when we talk about integration by types. Yeah. But you never have to know how to integrate something to check to see if the integral of something is equal to something else. What you do have to be able to do is differentiate the other thing. So the way we're gonna answer this question is by finding the derivative of x natural log of x minus x plus c, which we can totally do. So that's going to equal, let's say I've used the product rule here, so it's going to be the derivative of x times natural log of x plus x times the derivative of the natural log of x, which is 1 over x, minus the derivative of x, which is 1, plus the derivative of c, which is 0. And that looks like it's going to work out because x times 1 over x is 1. So I have the natural log of x plus 1 minus 1, which equals the natural log of x. That means yes, if the derivative of this is equal to the natural log of x, then yes, it's true that the integral of the natural log of x is equal to x natural log of x minus x plus c. So yeah, let me ask you all another question. So another true or false. Is the antiderivative of 2x times cosine x equal to x squared sine of x? Let's see. Work on that for a moment. Stuff over here. All right, so how do we check to see if an integral of a thing is equal to another thing? We take the derivative of the other thing. Again, that's not the only way you have to do it, but at this point, we don't know how to anti-differentiate this, so this is the only thing we have. And it's and even if you did know how to anti-differentiate it, the better way to check this is still by differentiating what we think is the antiderivative to see if we get back to where we started. And we definitely don't. Right? If we take the derivative of this, we should be using the product rule. And if we take the derivative of f times g, we're going to get f prime times g plus f times g prime, which in this case is going to be 2x times sine of x plus x squared times derivative of sine of x is cosine of x plus 0. And that's definitely not equal to x squared times sine of x. So definitely not. And I really want to emphasize this because it's something that comes up relatively frequently, is that when you anti-differentiate a product, we can't just take the antiderivative of each part and multiply it together. It doesn't work. And the reason is because of the product rule for derivatives, right? If you do that, and then you take the derivative, you need to take the derivative using the product rule, and you're definitely not going to get back to the thing we started with. On the other hand, we can show that the integral of 2x times cosine of x dx is equal to 2x sine of x plus 2 cosine of x plus c by doing the same sort of process. So let's check it out. If I take the derivative of this, the derivative of 2x cosine of x plus 2 cosine of x plus c. So here I am going to use the product rule again. The derivative of 2x is 2 times cosine x plus 2x times the derivative of cosine x is negative sine x. I feel like I might have made a small mistake here. Yeah, I might. Oh, I did. I wrote the. Oh, sorry. One sec, brain. That should be right. 2x cosine x, 2, 2, 2. Oh, because I literally wrote down the wrong. You guys see the mistake I made? I hope so. So the mistake I made is I wrote this here, and then I wrote a different thing here. I wrote cosine there when I should have written sine. Smooth, real smooth. So what I'm actually trying to check is that the derivative of 2x times sine of x plus 2 cosine x plus c is equal to 2x cosine x. So I'm going to use the product rule and get 2x times the derivative of sine plus the derivative of 2x times sine plus the derivative of 2 cosine x is 2 times negative sine x plus 0. And oh, look, the 2 sine x and the negative 2 sine x cancel out, and we're left with 2x cosine x. So oh yeah, question. I'm taking the derivative of this constant here. So you don't even really need to write that. I'm just trying to kind of be very showing all the things. But right, I took the derivative of 2x sine x to get this piece here, right? So just to back up, I did that's my f and that's my g. There's my f g prime. There's my f prime g. And then here's the derivative of 2 cosine x. And here's the derivative of c. Yeah. Yes. And one way to think about that is a constant function is a horizontal line, or that's one way of thinking about it. And what's the slope of a horizontal line? 0. So the derivative of a horizontal line is always 0. Just like the derivative of a straight line, like y equals 5x, is always whatever the slope is, which is 5 in that case. So yeah, constants always have a derivative at 0. I should be extra specific here. Constants on their own have a derivative at 0. Constant multiples do what I like to call hanging out, right? So if you were taking, say, the derivative of 6x cubed plus 5x plus 2, here we're going to get, and I'm going to write it out, even though we would usually just say 18x squared, I'm going to say it's going to be 6 times 3x squared plus 5 times 1 plus 0. So these constant multiples of functions hang out, whereas this constant on its own, its derivative is 0. And so then we would simplify that and say it's 18x squared plus 5. There was another thing over here. Sorry. So yeah, let's go that way. So let's recall, speaking of derivatives, let's recall our trig derivatives because we're going to need them to find their antiderivatives. So let's do it this way. Let's make a little list. Here's our function. Here's our derivative. So we know the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. Those are the easy ones. So, well, yeah, I'll just say that. And then the derivative of tangent x is secant squared of x, and the derivative of cotangent x is negative cosecant squared of x. And then we have secant and cosecant. The derivative of secant of x is secant of x times tangent of x. The derivative of cosecant of x is negative cosecant of x times cotangent of x. So we definitely want to know these. And then if we know these, we know the reverse order antiderivatives, right? If we know all this, then we can say, well, the antiderivative of cosine of x is equal to sine of x plus c, or the antiderivative of secant squared of x is equal to tangent of x plus c, or the antiderivative of, it gets a little harder when you have a negative one. The antiderivative of cosecant of x times cotangent of x is equal to negative cosecant of x plus c. So if you know a derivative, you know the reverse antiderivative. And we could write them all in here, right? We could also throw in, right, the integral of sine of x is going to be negative cosine of x plus c, and the integral of cosecant squared of x is going to be negative cotangent of x plus c, and the integral of secant of x times tangent of x is going to be secant of x plus c. No big surprises there, right? We know the derivative of secant is secant tangent. We know the antiderivative of secant tangent is secant. The only thing that's a little tricky here is the ones that are negative, right? So if you know that the derivative of something has a negative in it, then the antiderivative of that thing is going to kind of be negative as well. So the antiderivative of sine is negative cosine. The antiderivative of cosecant squared is negative cotangent. The antiderivative of cosecant cotangent is negative cosecant, but not too awful. However, we're not just limited to these. We're going to see fairly often things like the following. Yeah. I'm always like, do I want to leave this up here kind of, or do I want to just not? And it's never sure. So we want to maybe find the integral of something like cosine of 3x. And now this is where we're going to talk about how we can totally do a U-substitution here. And we should the first few times. But eventually what you're going to want to get comfortable with is being able to do this particular type of U-substitution without having to write anything down, other than what the answer is. So here, we're going to let u equal the stuff trapped inside the function, which is 3x. It's stuck. Now, the nice thing about letting u equal a constant multiple of x is it's always going to work out. Meaning, at least it might not be the right choice. Like it might not actually be easier to anti-differentiate the function, but you can always make the U-substitution process work and get to a new thing. Because when you let u equal a multiple of x, your du is just 3 or whatever that constant is times dx. And we can always isolate dx as just 1 over your constant times du. So I can rewrite this as the integral of, well, dx is 1/3 du, and cosine of 3x is cosine of u. So when we anti-differentiate this, we get 1/3 cosine of 3x. Oh, sorry. Wow. Why is my brain not working today? I am sorry. Wow. I'm really just trying to get to blow. Yeah. Wow. What's the antiderivative cosine of u? How about you all help me out? Which one is it? I realize. Yeah. I think my hearing is maybe going. All right. So 1/3 sine of u plus c. And then if we plug back in what u is, we get 1/3 sine of 3x plus c. And I know I've said this a few times, but I'm going to keep saying it. We see that if the function would have made you multiply by a constant when you took its derivative, so like the derivative of cosine of 3x would be negative sine of 3x times 3 because of the chain rule, the antiderivative is going to end up making you divide by that same constant, which makes sense because if we took the derivative of this, we'd end up having to multiply by 3 because of the chain rule, and we need that to cancel out with that 1/3 there. So without doing any work, we should be able to say, well, the integral of cosine of 3x dx is 1/3 sine of 3x. The integral of cosine of 7x dx, I feel like you could all write down the answer without actually doing any substitution. I'm going to give you a moment to do that. Should be getting 1/7 times sine of 7x. And we can check, right? If you want to check, we can take the derivative. The derivative of 1/7 times sine of 7x plus c is 1/7 times the derivative of sine of some stuff is cosine of the stuff times the derivative of that stuff plus 0 because the derivative constant is 0. And oh yeah, of course, the 1/7 and the 7 cancel out. So, excuse me, when you have this sort of thing you could choose for u, but it's just a multiple of x, you can kind of get away without doing the work. In a similar way, we could show that, or we can see that the integral of secant squared of 6x, well, I know that the integral of secant squared of x is tangent of x. So the derivative of tangent of x is secant squared of x. So here, I'm thinking it's going to be, wow, tangent of 6x. But what do I need to divide by? Well, I'm going to multiply by 1/6 or divide by 6, right? You can say it either way. I know you meant multiply by. Yeah, so we're 1/6 times tangent of 6x plus c. Or the antiderivative of secant of 8x times tangent of 8x is going to equal, well, I know the antiderivative of secant x tangent x is secant of x. So the integral of secant 8x tangent 8x is going to be secant of 8x, and then I need a 1/8 out in front. So these are what, oh yeah, question. That's a terrible, that's a great question. It's a terrible integral. So you're almost never going to encounter something like that. The exception might be, and I will, yeah, so fair question. I don't know if that's, I'm sure it's maybe doable, but it sounds very challenging. The thing you might see at some point is something like sine of 4x times cosine of 6x. And if you have to do something like this, there's a terrible trade-in you can use. I literally don't know what it is. Not because I've never seen it, because it's just one of those formulas that will not stay in my brain. So I'm pretty sure it's in the book, but this one, they're got like, so holy smokes, I should know the trade-in. I've seen some. So it comes from the fact that, wow, I know there's a way to do this, and I've literally like always gotten it wrong my entire life. This is one I've never liked, but there is a formula. There's now I feel like I owe you an explanation of how this works. So the idea here is that you can use the fact that sine of A plus or minus B equals sine of A cosine of A plus or minus cosine of A sine of B. Sorry, that should be a B there. Apologies. And cosine of A plus or minus B equals cosine A times cosine B minus plus sine A sine B. So there's a way to use these two formulas to make this thing happen. And wow, yeah, I want sine of A times. So I want to use this formula here. So I think what I want is something like, oh gosh, yeah, it's terrible. I don't really like it. You're trying to make that come out. So you want like sine of 4x minus 6x. That's going to equal sine of 4x cosine of 6x minus cosine of 6x times sine of 4x. And then I think you also want like, gosh, how do you make that happen? I don't know, magic. You do something else. It's really like, to me, these are the worst. So honestly, like, why should you spend time trying to figure this out when you can actually look up the formula? Now, I know that's not great advice all the time, but sometimes it is. This one, I'm so like not a fan of this problem. But I suppose we can also look at, it's probably something like this. So this would be sine of 4x times cosine of 6x. Oh yeah, I think I might have stumbled upon it. Plus cosine of 6x times sine of 4x. Wow, I magically got there because I lucked out. And then if you add these together, look what you've got. You've got sine of, well, let's see, sine of 4x minus 6x is sine of negative 2x plus sine of 4x plus 6x is sine of 10x. And it's equal to this plus this, which is 2 sine of 4x cosine of 6x. And this plus this is 0. It's a dumb, like, I don't like this question. You might have noticed I don't like this type of problem. But then we divide both sides by 2. And so the identity you can use is that this is equal to the integral of 1/2 sine of 10x minus sine of 2x. I'm using another identity there. The sine's an odd function, and sine of negative 2x is equal to negative sine of 2x. So you could do that. Actually, back that up. If you have this problem, you have to do that. There is no other really, that's not true. There's a weirder other way of doing it. You should do it this way. So to answer your good question, but also terrible question in that the actual integral that you're asking you is terrible. Sometimes you see things like this, they don't come up that much. Most of the time, this is not the kind of problem people are asking. But if you see this thing where you have trig functions with different arguments in them, usually it means you have to use some terrible trig identity like this. Yeah, that's what it is. And then you could, and so then I should say, then we can actually do it, right? This is totally not hard to do. Once you get to here, you're going to get 1/2 times the antiderivative sine of 10x is going to be negative cosine of 10x divided by 10. And the antiderivative sine of 2x is going to be negative cosine of 2x divided by 2. Plus c. So at least once you get here, we can still use this idea of the mini U substitution, where you're just saying, oh yeah, I could do a U sub for U equals 10x. I don't need to do a U sub for U equals 10x. So I know I'm just going to dividing by 10. All right. Okay, sure. Time. All right. So where I really kind of wanted to go with this, oh, it's going to require one more thing. I need one more thing. One more thing. Okay. So let's talk about one integral I've kind of avoided a little bit. Actually, before I talk about that, let's remind ourselves the antiderivative of e to the x is certainly e to the x plus c. And so we could also, so realize that for any function you know how to integrate, this idea of having just a constant multiple of x is always going to be there. So any trig function, if you have like a trig function of 3x, you're just going to divide by 3 when you do the antiderivative. Or for something like e to the x, if you have the integral of say e to the 4x, it's going to be exactly e to the 4x divided by 4. Let's see. Or if you prefer 1/4 e to the 4x. Let's see. Or if you're anti-differentiating e to the negative 2x, it's going to be e to the negative 2x divided by negative 2. Or negative 1/2 e to the negative 2x, if you like it that way better. But it's still the same idea of just dividing by whatever the coefficient of x is. Now, a couple things I want to make absolutely 100% clear. This only works if the thing you would be choosing for u is just a constant times x. As a counter example, we definitely cannot do the integral, say like e to the x squared is definitely not e to the x squared divided by 2x. Right? It's not just your stuff divided by the derivative of your stuff. Because if you took the derivative of this, you'd have to use the quotient rule. And it's definitely not going to be that. The derivative of e to the x squared over 2x is 2x times e to the x squared times 2x minus e to the x squared times 2 all over 2x quantity squared. I'm pretty sure that's not equal to e to the x squared. I'm 100% sure, not just pretty sure, 1000% sure. Really interestingly, actually, this integral has no antiderivative. There is no nice function whose derivative is equal to e to the x squared. If you throw this into something like the Wolfram integrator or some sort of other integration problem, it'll give you some function that's like I of x or whatever, and that just means it's the integral of your thing, right? So they're just writing this as like integral. Now, people still talk about evaluating this integral from like negative infinity to infinity, or actually e to the negative x squared, because this is a version of your standard normal distribution. So if you've ever taken a stats class and you've seen like the bell curve, that bell curve comes from the e to the negative x squared function. So even though we can't actually find the antiderivative, there's still a lot of time and effort spent in calculating like the area under that curve, because it is a very, very important curve in statistics. But what I was getting at was the following. There is one power of x that we actually haven't dealt with its integral. So we know how to anti-differentiate x to any power, right? You just add 1 to the power, divide by the new power, except for that power of x. Because if you add 1 to the power and divide by the new power, you're going to be divided by 0. So the thing is, we totally know what the antiderivative of this is. It might be easier to see if we rewrite it as 1 over x. So what's the or I should really ask, what function has a derivative that's equal to 1 over x? Yeah. Now, I'm going to throw in a little extra something because it's supposed to be there. It's actually the natural log of the absolute value of x plus c, not just x. Now, there's a couple ways of justifying this to ourselves. I'm going to tell you 2 of them. One way is that the domain of an antiderivative shouldn't really be smaller than the domain of the function it's coming from. This function 1 over x has a domain of every real number except for 0. So if you look at f of x equal to 1 over x, it looks like this. And the domain is every real number except for 0. The antiderivative, which is the natural log, I'm going to write natural log of x for a second just to kind of show you how that's not really going to be good. That function looks like this. And the problem is the derivative of this is fine on this side, but on this side, the derivative of this side should give you this part here. But we're kind of missing that whole thing. So what we do is we say, well, okay, if we throw absolute values there, then x can be negative. And it's actually going to look like a reflection, right? If you if we do that. When I plug in -1, I'm also going to get 0. I'm never good at drawing the left-hand side of this. It should look like a reflection of it. It's okay. It could be better. Those should be symmetrical. Now they're good. Now they have the same domain, which is what we want. Now, why would this be true? Like, I can't just throw an absolute value around something and say like it's the same because I said so. It actually is the same. So I'll remind everybody of a couple important facts. The absolute value of x is equal to x if x is greater than or equal to 0. Right? Absolute value of 5, 5. Absolute value of 7, 7. Absolute value of 0, 0. So if you have a positive number that you're taking the absolute value of, it just stays the same. No changes at all. But if the thing you're taking the absolute value of is negative, the absolute value of -5 is +5. The absolute value of -7 is +7. And the way we change a negative number into a positive number is by multiplying it by -1. Which we usually just write as -x if x is less than 0, +x if x is greater than or equal to 0. I know it always feels weird. You're like, why are we making it negative? We're not making it negative. We're taking a number that's already negative and multiplying it by -1 to make it positive. But it always feels kind of backwards. So this is how the absolute value function is defined as a piecewise function. And you know the graph of it, or maybe you don't, you probably do. Looks like a V shape like that. Y equals x over here, y equals -x over here. So then let's check out the natural log of the absolute value of x as a piecewise function. The natural log of the absolute value of x is going to equal, well, it's going to equal the natural log of just regular x if x is positive. We're not going to include 0 here because we can't take the natural log of 0, right? Natural log of 0 is still undefined all the time. But now we're going to let x be negative and then turn x into a positive thing so we can take the natural log of it, right? Because you can always take the natural log of a positive number. We can never take the natural log of a negative number. So even though it's going to look kind of funky, we're going to take the natural log of -x, because if x is negative, then -x is positive. All right, great. So let's check out the derivative now. So now the derivative of the natural log of the absolute value of x is going to equal. So what's the derivative of the natural log of x? Right. So it's going to be 1 over x if x is greater than 0. Now, what's the derivative of the natural log of some stuff? I said the magic word stuff. Well, it's 1 over, I mean, you're not wrong, but we should show all the work to get there. It's 1 over the stuff, which is -x. But then what do I have to multiply by? Which is right. So that's going to be 1 over x. So interestingly, whether x is positive or x is negative, the derivative of the natural log of the absolute value of x is just equal to 1 over x. So this really does actually show that the antiderivative of 1 over x should be the natural log of the absolute value of x, because the derivative of the natural log of the absolute value of x is equal to 1 over x. Yeah. No, we cannot. It is undefined. Yeah, yes, excellent observation. That's exactly why I didn't put the equal sign here, because x can't be 0. Very, very good. Yeah. It's kind of interesting. So when you think about like graphing stuff, specifically when you think about vertical asymptotes, most of the time, like almost all of the time, when you have a vertical asymptote, it's because the function has division by 0. The one exception, at least that I've seen over the years, is the logarithmic function. The natural log or log base 2 or log base 3, those functions also have vertical asymptotes, but it's not because you have division by 0, it's because you have this kind of other way of being undefined. But yeah, so logarithmic functions, you can never take a log of 0. And one way to think about that is, I know that when I like write something like y equal to log base 2 of x, that's equivalent to 2 to the y equal to x. So if I was going to try to find, say like x equal to the log base 3 of 0, like pretending like it actually existed, I'd be trying to solve, or that would be equivalent to 3 to the x equal to 0. But there isn't any x value where 3 to the x is equal to 0, right? 3 to the x is always going to be a positive number. So we can't solve it, which means, oh, this first thing doesn't really make any sense. Yeah, it's a good question. So what time is it? This clock here is killing me. It's showing it says it's 12:02 here. And I'm trying to figure out before class like how to change this to the right time. It doesn't. I'm sure it's possible somehow. It is not immediately obvious. So where was I going with this? I was going over here. So the integral of 1 over x is definitely equal to the natural log of the absolute value of x plus c. And the antiderivative of 1 over, say, something like 2x plus 3 is going to have a similar antiderivative. But here we probably should do the U-sub because it's going to be a little tricky. So let's let u equal 2x plus 3. Our du is going to be 2 times dx. Or as I would prefer, 1/2 times du is going to equal dx. So let's see, rewriting my integral here. I'm going to have the integral of, well, dx is going to be 1/2 du. That's my dx. And then I'm going to have a 1 over u. Okay. 1/2 sticks around. That's a multiple. And then the antiderivative of 1 over u, well, just like the antiderivative of 1 over x is the natural log of the absolute value of x, the antiderivative of 1 over u is going to be the natural log of the absolute value of u. So then we're going to get 1/2 natural log of the absolute value of 2x plus 3. Let's see. Oh, sorry. In a similar sort of way, we could ask ourselves, what's the antiderivative of x squared over x cubed plus 1? So this one might seem a little less obvious that we're going to get a natural log, but we are. So I'm still thinking, making a choice for you where my u is stuck. Which thing is stuck? The x squared or the x cubed plus 1? I know it's not as obvious when there's like no powers or functions or anything, but really the being in the denominator is another way of being stuck. You're stuck there. You can't really get out of the denominator in any meaningful way. So we're going to pick u equal to x cubed plus 1. And our du is going to be 3x squared dx. And just for a change of pace, I'll do this one in the way I wish the wishing I had the thing that I want kind of way, where I'm going to take my integral here and multiply by both a 3 and a 1/3, just in case you like doing it that way better. So then, oh, look, I have a 1/3 times the integral of my 3x squared dx is exactly du. And my x cubed plus 1 is exactly u. And actually, I wanted to write it this way so you get used to seeing it. I really don't love thinking about the integral of du over u. It just feels not nice to me, but people are going to write this 100%. I just want you to know that you can rewrite this as the integral of 1 over u times du. You don't have to, it's not required, but if it makes it easier to see what's happening, I recommend doing it. I do it for myself. I'm like, du over u, 1 over u, oh yeah, the integral of 1 over u is the natural log of the absolute value of u. And then I plug back in what u is, and I get 1/3 natural log of the absolute value of x cubed plus 1. The absolute values do matter. You do need to put them there. Sometimes you might, well, let me show you one more example just to kind of go along with that. So if I was integrating 2x over x squared plus 1, trying to make it very obvious that our choice should be u equal to x squared plus 1. And look, our du perfectly works out. Our du is 2x dx. We couldn't be more happy about that. It's the ideal situation. So this is going to end up being the integral of, once again, du over u. And I'm not going to write it as 1 over u this time, just so you can get used to seeing it. Say, well, it is 1 over u. The integral of 1 over u is the natural log of the absolute value of u. And then if we plug in our u, it's the natural log of the absolute value of x squared plus 1 plus c. Now, what I actually want to say about this is if you're like looking at a solutions manual and you see this problem, you'll probably see the answer written in the following way. The natural log of the not absolute value of x squared plus 1 plus c. Why wouldn't I write the absolute value there? The reason is x squared plus 1 is always positive no matter what x is. So I don't need the absolute value there because the stuff inside never is negative anyway. So if you have an expression where the inside or the argument of the logarithm is always positive, you can drop the absolute value. You often see textbook solutions drop the absolute value there. So if you're wondering what happened to the absolute value, you should ask yourself, oh, is the inside always positive? Oh, then they drop the absolute value because they wanted to, because they can. But I would, if I was writing answers to things, I would certainly encourage you to err on the side of caution. If there's supposed to be an absolute value there, just write it. There's no need to drop it. It's still perfectly correct to write it that way. So I would encourage you to write it that way. So yeah, what I wanted to do was, where'd you go? All this little handout. So I really can't stress enough, but also how much I want you to be good at finding antiderivatives of things that require very minimal or what I call mini U-Substitutions. So I'll put this up on. Should put that up there before I oh, so here are some things that I would like us to be able to anti-differentiate without having to do too much work. Hopefully people on Canvas can see this all, or on Zoom can see this all right. That's fine. So let's actually start over here on the right. We've done some of these already. The integral of cosine 4x, we know is going to be sine of 4x divided by 4. That's a constant. Because, well, right, the derivative would be cosine of 4x times 4 divided by 4, and the 4's cancel. And the same thing's going to work for each of these. The antiderivative of cosine of 1/2 x is going to be sine of 1/2 x divided by 1/2 plus c. Now, I think we all can agree we shouldn't leave it like that. Dividing by 1/2, terrible. We should write it as times 2. That's 2 times sine of 1/2 x plus c. And same deal here, right? So right, the pattern is the same every time, right? The antiderivative of cosine of negative 3x is going to be sine of negative 3x divided by negative 3 plus c. The antiderivative of cosine of ax is going to be sine of a times x divided by a plus c. You could check, right? We could totally, for any one of these, have done, like for this first one here, we could have said, oh, I'm going to let u equal 4x. My du is 4 times dx. My 1/4 du is dx. And then the integral of cosine of 4x dx becomes the integral of cosine of u times 1/4 du. And then that's going to be sine of u times 1/4 or divided by 4, see, which is sine of 4x divided by 4 plus c. I really don't want you to write that out every time, right? Not because you're not allowed, but because I don't want you to waste your time or spend your time doing it. Now, it's not a waste of time if you're doing it because you need to do it, right? You totally should. If you're like, I see cosine 4x and I'm like, don't remember what to do the U-Substitution. but really you're going to see so many of these small U subs, it's going to be worth the mental investment to make sure you can do these without having to write it all out. So let's look at the sine ones. Same idea. The antiderivative sine of x is negative cosine of x. So the antiderivative sine of 3x is going to be negative cosine of 3x divided by 3 plus a constant. Same deal here. The antiderivative sine of negative 2x is going to be negative cosine of negative 2x divided by negative 2. And of course, I would do the extra step of simplification here and write it as cosine of negative 2x divided by 2 plus c. It is worth your time to do that. For cosine of x over 4. So for cosine of x over 4, it is important to recognize that that's, for sine of x over 4, it is important to recognize that that is sine of 1/4 times x. So that we can say, oh, I have my antiderivative is going to be negative cosine of 1/4 times x divided by 1/4, which again, we should simplify as negative 4 times cosine of x over 4. So it's repetitive, right? I know we're seeing like the same thing over and over and over again, but that's because we're really trying to drill it into ourselves that, oh, we do this antiderivative of a thing as a constant times x, we're just going to divide by that constant. Same deal here. The antiderivative sine of a constant times x is negative cosine of that constant times x divided by that constant. Oh, itchy nose. All right. Same deal for this next column, right? The antiderivative of e to the 3x is e to the 3x divided by 3. The antiderivative of e to the negative 2x is e to the negative 2x divided by negative 2 plus c. This one, the antiderivative of e to the x over 8 is e to the x over 8 divided by what? Yeah. And then I do think we should simplify that as 8 times e to the x over 8. Let's see. And the antiderivative of e to the ax is e to the ax divided by a. So now is where things get slightly trickier. For the integral of 1 over x plus 5, when I see the antiderivative of 1 over x to the first power plus a constant minus a constant, doesn't matter. I'm thinking it's got to be the natural log. It's the natural log of the absolute value of x plus 5 plus c. And that works because what's the derivative of the natural log of x plus 5? Or I should say, what's the derivative of the natural log of some stuff? It's 1 over the stuff times. And what's the derivative of the stuff in this problem? Just 1. So it works. The derivative of this is 1 over x plus 5 times 1. Great. So now for this next one, I've got 1 over 2x minus 3. I'm pretty sure the antiderivative is the natural log of the absolute value of 2x minus 3. But if I took the derivative of that, I would get 1 over my stuff, 1 over 2x minus 3. And then what would I have to multiply by? 2. But I don't have a 2, so I need a 1 over 2 to account for the 2 that I would have to multiply by. So just like these other situations, when we have an integral of a constant multiple of x, plus or minus a constant, we end up dividing by the constant multiple of x. Same idea in this next one. This is going to equal the natural log of 6 minus 3x. And then what constant multiple am I going to have to divide by? Yeah, good. You got the negative. I'm going to have to divide by a negative 3. What time is it? Okay. And then same idea here. If I take the antiderivative of 1 over ax plus b, it's going to be the natural log of the absolute value of ax plus b. And then I need to divide by a. Because my derivative is making me multiply by a. In fact, I should point out that for each of these, like kind of last ones here, you could have actually thrown on a plus b to any of them. So for example, it's also true that the integral of e to the ax plus b dx is still e to the ax plus b divided by a. Because when you differentiate e to the stuff, you get e to the stuff, which is e to the x plus b, times the derivative of the stuff, which is, and here the antiderivative of sine of ax plus b is going to be exactly negative cosine of ax plus b divided by a. And here the antiderivative of cosine of a multiple of x plus a constant is going to be exactly sine of ax plus b divided by a. So I know I've said it like 16 times in these 16 examples, but when you anti-differentiate something where you have a constant multiple of x, we just end up dividing by that constant multiple.